Coming to transformer core, transformer winding and transformer insulation. Transformer core is a electromagnetic laminated iron core. This core is prepared mainly by laminations. These laminations can be cast iron, cast steel, mild steel, silicon steel, and CRGO steel. As the quality of the material increases, flux density of the material also increases. For example, silicon steel having flux density of 1.2 Tesla, whereas CRGO is having 1.6 Tesla or even 2 Tesla. MRI machines, nowadays we are having 2 Tesla MRI machines. As the flux density increases, size of the machine also decreases. So that means by increasing the flux density, we can minimize the area of the machine. So flux density is inversely proportional to area of the machine. This total iron core is a laminated iron core. Why laminations are provided? The laminations are provided in order to minimize the eddy current losses. These laminations are insulated from each other. So at a nearly 50 Hz frequency, the thickness of each lamination is around 0.35 mm. These laminations are insulated from each other with insulating material. The type of insulating material can be paper, lead oxide. The advantages of mica is it can withstand very high temperatures. All these laminations along with insulation are stacked together. So why we need to stack these materials? In order to reduce the air gap between the laminations. What if the air gap is high? If the air gap is high, then the reluctance offered by the magnetic core is increases, and the magnetizing current required by the source to establish the main field flux in the transformer, that also increases. So in order to minimize these effects, these cores are stacked together. This is the total internal structure of iron core. That is a crystalline body-centered cubic structure. This is completely a ferromagnetic material. So this ferromagnetic material will be having low hysteresis losses. The hysteresis losses, according to formula, that depends upon x to the power of 1.6. This depends upon type of material. These magnetic materials are having low reluctance, high permeability. The permeability means the ability of allowing the magnetic fluxes through the material. mu equals to mu naught mu r. If we take the material along the edges, the permeability is high, and along the diagonals, the permeability is low. Different types of transformer cores. One is core type transformer, second one is shell type transformer, third one is stepped core or cruciform core. These are the different type of transformer cores. These transformer cores are prepared with different shapes stacking together. The shapes can be I shape, L shape, E, U, T, different types of shapes. So these are the different type of shapes, I shape, E shape. These shapes are stacked together and made a complete square or rectangular form in order to prepare continuous core. So these kind of shapes are required to prepare core type transformer and shell type transformer. But for cruciform type transformer or step type transformer core, this type of arrangement is not required, whereas square of different sizes can be fabricated and can be stacked together to form a cruciform section or stepped core. So this is stepped core, this is normal square core, and this is nearly circular core. The advantage of nearly circular core is insulation can be minimized, windings can be minimized, total weight of the transformer and cost of the transformer also reduced. So these are the advantages of stepped core. The stepped core, the core is almost nearer to circular shape. The number of steps can be varied from 2 to 3 or even 5 steps also. So the advantages are less insulation, less copper, less weight, smaller size, and low cost. Hysteresis eddy current losses also be minimized. So these are the advantages of stepped core. And utilization factor, this is the ratio of effective cross-sectional area to total cross-sectional area. Here the core shape is varying from square to circle. So the effective cross-sectional area will increase. The utilization factor ratio is around 0.8 to 0.95. This type of transformer core mainly used for very large rating MVA transformers. This will increase the efficiency of the machine. So the total area of core, which is equal to net core plus insulation, which is the dielectric material placed in between the sheet steel laminations. Gross cross-sectional area equals to net cross-sectional area plus insulation. The insulation is approximately only 10% of the volume of the core. Remaining 90% volume is sheet steel laminations only. Here comes the stacking factor. Stacking factor is the ratio of net cross-sectional area to gross cross-sectional area, that is 0.9. It is lesser than 1. Size of the transformer core with reference to flux density. The relation is inversely proportional. As the flux density increases, area decreases. This is the graph of pH curve. P is the flux density, H is the strength of magnetizing flux, Im is magnetizing current. B equals to mu naught mu r H. That means B is directly proportional to H. The relation between B and H, it has to be linear, but after a certain point, the break-even point, the relation is saturated. That means the core is going into saturation region. So far, we had discussed about transformer core. Now, we will discuss about transformers, windings, insulations. So next to transformer core, first LV insulation is placed. After that, LV windings are placed. After that, HV insulation. After that, HV windings. These transformer windings can be placed on both the limbs. 50% of LV winding and 50% of HV winding can be placed on both the limbs. This type of arrangement is known as concentrated arrangement. The winding is arranged in cylindrical forms. The advantages of concentrated or cylindrical type of winding arrangements is low leakage flux, high coefficient of coupling, low insulation requirement, low copper requirement, weight is low, size of the machine reduce, cost of the machine will also reduce. These are the advantages. This is core type of transformer and this is shell type of transformer. In case of shell type of transformer, the windings are placed in sandwich form. First LV insulation, next LV winding, next HV insulation, again HV winding, and so on. So in this way, the windings are placed on the transformer core limbs along with insulations. So these are the transformer core limbs and these are the insulations along with windings. These terminals will be brought to the bushings. Tappings mostly provided on HV winding only. HV windings are placed on outer layer on the transformer limb so that tapping can be taken easily. So the secondary terminal voltage can be controlled by varying the tap positions of the primary winding. Winding placements on transformer limbs and type of forces. For example, we are considering total HV winding is placed on limb 1, total LV winding is placed on limb 2. But in this arrangement, 50% of LV winding and 50% of HV winding both are placed on each limb. In this type of arrangement, the type of force is attraction force. In this type of arrangement, the type of forces is repulsion forces. This is primary side and this is secondary side. To the primary side, currents are entering on the top and flows through the winding and returns from the bottom. Whereas on the secondary side, the currents are returning from the circuit from the bottom and travels along the winding and returns to the circuit from the top side. So this is generalized current direction. Based on this generalized current direction, and if we apply right hand thumb rule, the type of flux direction or current direction in the windings represented with dot and cross method. These are the representations. The windings are represented with two circles on either side. So with reference to right hand thumb rule, for inner side windings, it is dot. For outer side windings, it is cross. Similarly, on the second limb, for inner limbs, it is dot. For outer limbs, it is cross. Compare the statement. On one side of transformer limb for HV winding and LV winding. So on one side means here we are considering either outer side or inner side. If we take the inner side, both the directions are dotted directions. Both are inner sides. Again, if we consider right hand thumb rule, the dot means pointing out. So the direction of fluxes in upward direction. Here the dot is pointing out. So again, the direction of fluxes are downward. So these two cross each other. So inside the core, the net force is 0. But from outer sides, the net forces are towards the center of the core. So finally, the net forces inside the core are 0. But the net forces from outer side, it is towards the center of the core. Final force is attraction force. In a single statement, when windings are placed on opposite limbs, fluxes will be in the same direction. That means inner side or outer side on both the limbs in same direction. Here, the inner side, the directions are same. The outer side, the directions are also same. That means when the windings are placed on opposite limbs, the direction of fluxes are in same direction and the type of force is attraction force. Similarly, when windings are interleaved or the windings are concentrated windings, then 50% of LV winding and 50% of HV winding are placed on each limb. That means windings are placed on the same limb. Then the fluxes are in opposite directions. This is the LV winding. This is the flux direction dot. This is the flux direction cross. In HV winding, it is cross and it is dot. That means the flux directions are opposite. So the type of forces. This is dot, this is cross. This is attraction force towards the core, and this is cross and this is dot. The type of force between these two windings is repulsive force. This is outwards and this is innerwards. So the net force is repulsive force. So these are the types of forces. Depends upon windings placements. So far we had discussed types of core, insulations and windings. So we had completed the basics of transformer core, insulations and windings.